Good morning, my lovely 13s. Right, buddies, this is the lesson that you have all been waiting for. It is the lesson where I'm actually going to give you enough time to practice a whole bunch after the lesson. Well, fingers crossed anyway. So anyway, here we go. The title for today is Harmonic Motion and Damped Harmonic Motion. And before we actually start trying any of this, I've put this little box from last week. You do have this complete note from last week too, but it is yeah, it's every single different form you can get when you're solving these second order, linear, homogeneous, second order differential equations with constant coefficients. Yay! So there you go. This is all the formats it can be. With the auxiliary equation, you can have a positive discriminant, which makes them in this form because you have two values of lambda. You can have a discriminant equaling 0, so a repeated root, and on that one you get them in this form here, which is, yeah, just another form for it. You can get purely imaginary if, yeah, if it's just imaginary. You can get imaginary answers out, or you can get complex answers out, and these are all of the different formats that you can have, okay? So that's the most recent thing that we've done. If you already got that note written, there's no need to write it again if you've got it somewhere handy, but if you didn't make a note of it last time, make a note of it now. Okay, cool beans now, buddies. Let's get a quick start. So, okay, so basically the only new thing that we're doing today is we're going to be drawing the graphs, okay? So that's where the harmonic and damped harmonic motion comes in. So just to give you a quick rundown on it, because I think some of you will want to take, some of you probably do take physics, and some of you will be interested in things like engineering, like mechanical engineering, and actually engineering with physics as its focus as well. You'll be able to do lots of stuff with harmonic motion. So a nice, easy example that people use with harmonic, well, it's not a super easy example, but anyway, here's an example of harmonic motion. Say that you were to have like a mass, like just I don't know, just a mass of any sort, and you were to attach a spring to it on either side, so like a spring that's pushing on both sides it into the middle. Well, here's what you can do. You could pull your mass out toward the one side, so it compresses one string and it extends the other. Well, if you let that go, so if you pull it to one side, then let it go, it would fling all the way to the other side, but not quite, and then it would be pushed and flung back and forth to the other side, and it would end up going like left, right, 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 quicker, 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 until it got stuck right in the middle, back in equilibrium. Okay? That's damped harmonic motion because it's harmonic motion, because it oscillates, it's a real life thing, it's going back, forth, and it's damped because it's returning to an equilibrium position. The motion is decaying, is what they would say in physics, but you don't need to know any of that for what I'm doing, so I don't know why I want to talk on a tangent on that. But yeah, in case you're wondering what this is, that's what this is. Cool. So let's do it. It says, a damped oscillating system is modeled by the differential equation that, where k is a constant that can be varied. When t is 0, x is 0, and dx dt is 1, solve the differential equation for the following values of k and sketch the graph of the solution in each case. Okay, buddies, so you can do everything but the sketch at this point, just because I want to make sure that well, you probably could do the sketch. This is what I mean. You'll get lots of chance to practice today. But, yeah, let's have a go. Let's do it. Okay, so you can do pretty much everything. So if you feel like you want to get ahead of me, you can go right ahead of me all the way to the sketch, if you like. So pause and wait for me at the sketch. Go. Okay, and if you want to stay with me instead, here we go. So for part I, which we're just going to do I on this slide, it says k is 126. So I wonder if you remember the first step. Yeah, that's it. You found the auxiliary equation. So the auxiliary equation in this case is going to be lambda squared plus k lambda, but k is 26, so 26 lambda plus 25 equals 0. Okay, so we don't know anything about it yet, about the discriminant or that, so we'll just try to solve it. Oh, it does factorize, hooray! Two numbers that times 25 add to 26, it's lambda plus 25 and lambda plus 1, which means that we are in the lovely scenario that we have lambda equals minus 25, and we've got that lambda equals negative 1. So we're in one of those two solution scenarios, which means which of the four is it? Well, yeah, well, it's the top one, of course, because we've got these two guys together. That's how this works now. Now that you can do all of them, you just have to know which one to put it into. So here we go, general solution. Okay, which means, and it bothers me when they do this, it's not y and x, it's x and t. So x looks like it's the dependent, so it'll be the subject, it'll be x equals, And here we go. It's going to be a e to the minus 25t plus b e to the minus t. Cool beans? That's what we got. Oh yeah, so actually, you know that little spiel I just went off on about the spring and the mass and stuff? That would model this brilliantly. So it's time and it's a horizontal distance. That would model my thing I just told you about really well. Okay, so here we go. Next thing here, next is the particular solution. P-A-R-T-I-C-U. Oh, I forgot whole half the word. Particular. U-L-A-R. Okay, so the particular solution, my buddies. Well, let's do it. You just have to use these facts. So t is 0 means that x is 0. Well, let's do it. So just using the general solution here, you're going to get 0 equals a e to the 0. So it's just going to be a plus b. Cool beans? That's it. Now we got to get the other one. So for the other one, we'd like to use that when t is 0. Dx dt is 1. Dx dt is 1 to get the other equation. So we can figure out what a and b is. Well, let's do it. You're going to get dx dt. And we're going to get minus 25 a e to the minus 25t because of chain rule, minus b e to the minus t because of chain rule. Okay, now let's bodge our stuff in. So 1 is going to equal, this part's all just going to go, so it's going to be minus 25a minus b. Cool beans, but we know that, let's do it with a's. We know that a is equal to minus b, which means that we're going to get here, we're going to get 1 equals minus 25 times minus b minus b. So 1 equals, what's this going to be? Here we go. 25b, take 1b is 24b. So b is 1/24. Okay, so b is 1/24. There's the tricky part. Into there then. That means just that a is equal to negative 1/24. And shaboosh, there you go. That's what we knew from last time. So our particular solution is just going to be this. It's going to be x equals negative 1/24 e to the negative 25t, and then it's going to be plus 1/24 e to the minus t. Okay, so there you go. Happy days. There's our particular solution. So that's the answer to the algebra part of this question. But the new thing is the graph, okay, my buddies? Now, we've done graphs like this before, so this one won't be, this one won't be as terrifying as they will be in a moment. But let's do it anyway. Here we go. Okay, so to start with, you can rewrite it if you want. Yeah, I'm going to actually to make sure that we're all cool with this. I'll maybe skip some steps on the next ones though. Here's what you got. This is going to be 1/24e to the 25t, and then it's going to be plus 1/24e to the t. Okay, so what's going to happen here then, my buddies, is let's get our initial stuff in. We know it goes through 0, 0, so that's a point on it. That's from our condition that was given. We know the gradient's positive as it starts because it says that the gradient at t is 0 is positive. So it'll start up by going up, and then you just need to consider what happens at big neg. So limit as t approaches infinity, essentially, of your equation. Well, here's what you're going to get. This first thing here, it's going to go to 0 way faster. So see how this is 25t? So as you put numbers in, this one's going to get way bigger, way quicker than that one. So this is going to go to 0 first, which means that it's going to disappear altogether, which means we're going to be left with this, which will also go to 0, but at the positive side. All the way throughout, just using our sick graph skills, this is bigger throughout than the other one. Okay, this is bigger and this is smaller. Okay, this one goes to 0 first because the 25 is going to make it go smaller first. So yeah, that one's going to be bigger, which means at the end it's going to just be positive 0, which is a lot of effort just to say positive 0. The graph's going to look something like that, okay? And it's going to be asymptote at 0. And boom, there you go. That's not even oscillating or anything like that, okay? So that's just regular old, yeah, just a regular old one, that. Okay, there it is in autograph, just for you guys to see. So it looks it's because I had to make the scale really small, just because it went to 0 like instantly. So this is a small scale. So that is still a graph that's worth saying. We got the general shape right. It starts on a positive gradient. It goes up, peaks, and comes down. So that's okay. Our graph would have got full marks for that, even though it's not quite the same. Cool. Rightio, next one. K equals 6. Well, you can definitely do this one now. So if you want, just jump ahead of me and come back. And this is the most interesting graph. So don't try to do the graph on your own, but come back to me at the graph. Ready? Pause. Go. And if you're with me, here we go. Try it, try it, try it. First things first is the auxiliary equation. So let's do it. It's going to be lambda squared plus 6 lambda in this case. 6 lambda plus 25 equals 0. There's definitely not two numbers that times to 25 and add to 6, so it's going to be quadratic formula. So lambda equals negative 6 plus or minus the square root of, it's going to be 36, 6 squared, plus or minus the square root of b squared minus 4ac, minus 4 times 1 times 25. Cool. That's what we got there, all over 2a. 2 lots of 1. So lambda equals minus 6 plus or minus the square root of 36 take 25 is 9. If I got this wrong, I thought this was supposed to be a hard one. Oh, I do have it wrong. I didn't times it by 4, did I? Oh, and it's 11 and not 9. Yeah, I got that wrong for many reasons. Oh dear. I was about to say, this is like ridiculously too easy. Okay, no, I didn't. I forgot to times by 4. Okay, so let's check this bad boy out again. 36 take 4 times 25 is 100. 36 take 100 is minus 64. That's better. That's the nightmare I was hoping for. Over 2, which means that we're going to get minus 3 from this, plus or minus, and what we're going to get here is 8i divided by 2 is 4i. So again, we're in two solutions, but we are in a complex number situation. So just in case you don't remember from last time, I mean, I bet you do, because it's the same notation as you've used before. That's the alpha, and the thing that's touching the I, the complex part, is the beta. Oops, is the beta. Okay. Now, here we go. Into our general form. Now, you know that the general form is this, okay? So the real part touches the x, and the beta part is the is what's inside the trig, okay? So let's do it, let's do it, let's do it. Our general form, I'm going to run out of space on this one, I can feel it already. Our general form is going to be this. It's going to be x equals, because x is our dependent one again, e to the minus 3 t, open bracket, p cos 4t plus q sine 4t. I believe I have that right. I think it goes before sine, I'm pretty sure. Yeah, it does. Brilliant. Nice one. Okay, and that's what we got. So there's our general solution. On to the particular, my buddies. Particular. Okay, now if we want the particular solution, we just have to pop our values in. So let's do 0, 0 first. 0, 0. If we do 0, 0, then what we're going to find is we're going to get 0 equals, that's just going to be gone. Okay, this is just going to be 0 equals, that's going to be 1, open bracket. Cos of 0 is 1, so we're going to get a p, and sine of 0 is nothing. So we're just going to get the p equals 0 off of that one, it looks like. Cool beans, so there's where our p is. Now, the other one then, we have to use what was the other one again? We have to use that at t is 0, dx dt is 1. So here we go. Oh my god, nightmare. Okay, I'm going to be lazy, just like I was last time. I know that p is 0, right? Yeah, I'd like to bin that because I don't want to do so much product rule if I don't have to. So I'm going to bin the p0 part off. So to start with, x is equal to, I know p is 0, so that's just going to be gone. E to the minus 3t q, so q e to the minus 3t sine of 4t. Okay, so let's do it. dx dt. I've really not left myself enough room. I'm going to squeeze it, and then I'm going to go up there after. Okay, so here we go. It's going to be minus 3q e to the minus 3t sine of 4t. Sine differentiates to cos, so we're going to still be in a plus situation here. Plus q e to the minus 3t, so copy that and differentiate the second. Sine of 4t differentiates to 4 times cos of 4t because of chain rule. So it's going to be cos of 4t, but then you're going to times by 4, so the 4 is going to go there. Which means what we're actually going to have here, my buddies, with the numbers put in, so here we go, up and over, with the numbers put in, it's going to be on the left, 1, and on the right with 0. Sine of 0 is going to disappear altogether, so I'm just left with the second term. It's going to be 4q e to the 0 cos of 0. Okay, cos of 0 is 1, e to the 0 is 1, 1 equals 4q, q is a quarter. Okay, which means our particular solution is going to be this. It's going to be x equals e to the minus 3t times by, and remember p was 0, so it's just the second term. Q is a quarter sine of 4t, or in other words, just put the quarter in front. It's going to be x equals, I regret not leaving enough room, a quarter e to the minus 3t sine of 4t is what you're going to get off of that one there. Now, the question, the problem, the issue that we've got here, watch my 6 goes, group them, hold control so they stumble together, shrink them, oh yeah. Okay, look at the extra room. The problem that we're going to get here is the sketch. This is where it's a bit tricky, okay? Now, it's okay though. We're going to be able to actually do the sketch really nice, and this is actually your first cool one. Okay, sketch. And this is it. You ready? To start with, let's have a little look at it. First things first, there's trig in it, so let's get our graph ready. Actually, first things first, let's get our graph ready is a good idea. Okay, I'm going to explain the lovely, lovely sketching that there will be on with this. Okay. Number 1, there's trig in it, so it's going to oscillate, okay? Number 2 is, let's get our information in. So we still know that 0, 0 is a point on it, and we also know that the gradient starts off positive, so it's going to start by going up. Now, in the long term as well, so this thing you could write down to make it easier to understand or whatever, it's like a quarter e to the 3t on the bottom, and then that's just going to be timed separately by sine of 4t. Well, as t gets big then, my buddies, if you want to think of it in the red, like I've got it there, as t gets really big, this bottom of this fraction is going to get absolutely enormous, like ridiculously enormous. It's still going to tend to 0, okay? Now, that's the effect of this. It's going to be an asymptote at 0. We've already just discovered that, because that's what's going to happen as the number gets huge. It's going to go to 0. But the trouble is with the sine. What is sine going to do? Well, here's what you need to think, my buddies. I'm going to sketch it, and then I'm going to explain it from the sketch. It's going to look something like this. Okay, and then it's going to like hover and just get flat down there. That's what this thing's going to look like. So here's all the reasons why. So number 1 reason is because we had this given point, okay, at the start. The given point is there. We knew that that was a point on it. Yeah, get green. That's a point on it, so we know it starts there. Number 2, positive gradient. Number 3, it goes to 0 as it gets really huge, okay? So like the limit as x becomes enormous is going to go to, or as t becomes enormous, I should say, is going to go to 0. But the trouble is we don't know if it's positive or negative 0, and it's because it oscillates around sine of 4t. Now, I have to show you one final thing. The final thing I got to show you, buddies, is this. Sine of 4t usually goes between 1 and minus 1, right? So by having this thing in front of it, say it was a 2 in front of it, it would go between 2 and minus 2. Say it was an x in front of it, it would go between minus whatever the x value was and positive. This thing's actually going to get trapped as well. It's really cool, this. It's going to be trapped. I'm going to have to label all of this really nicely for you. Ooh, drat. Oh, I was doing so well. It's going to get trapped under this equation here. Okay, so here's what you've got. This is our actual equation. So this is actually, the red is actually this, okay? That's the actual differential equation that we're dealing with. But the sine wave is actually going to get trapped between the part that's not the sine wave. So it's actually going to get like oscillating between these two functions. It's going to be y's between like a quarter d to the 3x and minus a quarter e to the 3tx, whatever it was. Oh, that's x as well. But it's actually going to get trapped between those two. It's really cool, this, and I bet if you think about it, you could see why. It wants to go between 1 and minus 1, but instead it's being multiplied by its function itself. So that's it. That's your graph. It's an oscillating damped graph. That's the mass going between the two springs and slowing down as it goes. It leads to that. There it is actually drawn, okay, my buddies? So you can see there's the red and there's the 2. This is the real part of the auxiliary equation made the 2 blue lines. There they are, and the whole equation together is the red line. And that's what you got. Very cool, eh? Cool. Because I said I wanted to give you time to practice, I think I'm going to race through this. Let's do the auxiliary equation together, but I actually have notes on this, so I'm just going to copy the answer after the auxiliary equation. So let's do this final one, okay? Final one. I bet you can tell what's going to happen on this one potentially, but let's do it. Get the auxiliary again. Pause as well. Do it without me. Go, pause, and get the particular as well, because I'm going to skip the particular this time, so you don't skip it. You get a wriggle on. Okay, auxiliary equation to start with. Let's do it. Well, here we go. It's going to be lambda squared plus 10 lambda plus 25 equals 0. Okay, and oh my gosh, it's a repeated root. Surprise, surprise. The two numbers are 5 and 5. Lambda plus 5 squared equals 0, which means that lambda is equal to 5, but or negative 5, I should say. Lambda is negative 5. But it's a repeated root, okay? Okay, so knowing that, which one does it go into? Yeah, well, the second one, you know about that. The general solution, which one does it go into? It's going to go into this one. It's going to be the a plus bx one. A plus bx e to the minus 5t. So there you have it. And again, to remind you, it's this one, right? Repeated root. Cool? So there you go. It's that one, okay? To get the particular solution, you're going to do all your bits and bobs, and you're going to end up with a particular solution, okay? And the particular solution, because I am cutting to the chase to not spend too much time on it, is this. You're going to get x equals t e to the minus 5t, okay? But you have to do all the steps to get that. But that's what you end up getting as your particular solution. Cool beans? Okay, let's try the graph then. Let's see if we can logic our way through this graph. Okay. So we've seen what happens when we've got a complex one. We've seen what we've got when we've got two solutions. Now we can see what we've got when we have a critical... Oh, I just gave away the answer. We can see what it is when we've got the... when we've got a repeated root. So let's do it, my buddies. Well, let's start off with everything that we know. So start with, 0, 0 is a point. It's got a positive gradient. It heads up. And now we just need to consider its behavior as it gets really big. So instead of saying big neg like I normally do, let's do it. X goes to infinity because we're posh we are as t as well. We're posh we are. We're for the maths ones. We use proper notation. So the limit as t goes to infinity of the function x is going to be, we'll have to just consider it. Okay, if you want to write it in a format that you can understand it better, here you go. X equals t over e to the positive 5t. You just got to say to yourself, my buddies, which of these is going to grow faster, t or e to the 5t? Which one is going to make a bigger number when you put a big number? And if you put 100 in, which one of these is going to be bigger? Well, e to the 5t is way, 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 or like so much bigger. So essentially, it goes to 0. Okay? Is it going to oscillate? Well, no, actually, it isn't going to oscillate. It's just going, because there's no trig in it to make it oscillate. There's no reason that it would become negative. Like, at what stage could this become negative when you're putting positive numbers in? Well, never, ever, ever. So it's going to be like this, straight up, sharp, shock, and down, like that. Okay, so it looks exactly the same as the first one, which is a bit of a problem because this type of question looks the same as the first one. There it is with an actual graph. What we've done is absolutely acceptable as well, though, okay? So you don't have to be able to draw it super accurately. Cool. So here you go, my buddies. That's literally it. The only new thing was about drawing these guys and drawing them relatively well, okay? So, yeah, happy days. I think I just made a mistake on this. Oh my god. Yeah, sorry about that. Did you see that this should be negative, right? Because it has to get smaller, doesn't it? I forgot the negative in front of those threes. Sorry about that, buddies. Otherwise, it would get enormous, right? It would be exactly the opposite. It'd be up like that and down like that. So yeah, so I forgot the minus, but yeah, that's it. So hopefully that's okay. You've got three different scenarios it could look like. The first and the third scenario look the same pretty well, and the second one looked really different. Cool. Just some terminology. Overdamping, my buddies. Overdamping is when you get the discriminant as positive, okay? So discriminant's positive, but the roots have to be negative. Now the reason why the roots have to be negative is you need it to decay, okay? So if you check out our first one, see how our roots were both negative, negative 25 and negative 1. If it wasn't negative, then these guys wouldn't go to 0. Get me? The reason why this thing tailed off to 0 is because these both became 0. So it has to be negative roots, otherwise it gets bigger, not smaller. So overdamping. Discriminant is positive, but the roots are negative, so the function decays. It just dies out without oscillation. Cool? Underdamping. Now that is our oscillating one. That's our really cool one, and it just means that the auxiliary equation is negative. Yeah, the positive negative bouncing comes naturally. Yeah, it comes naturally because of the trig. These two lines, the two dashed lines, are to do with the real part. So just like what we said before, when you draw it, you should label what those two lines are, and they're to do with the real part. Okay, they're the real part of it, not the p cos theta plus q sine theta part. These are the a e to the alpha x part that makes them two. One positive, one negative, to account for the negative of the sign. You have one of them under, one of them over. Happy days. And critical damping is when you get the repeated root. It's the one that's exactly halfway between these two, because if the number was a little bit smaller, it'd be underdamped, and if the number was a little bit bigger, it'd be overdamped. So it's exactly between. So you can't really tell from the graph, and that's that. But if you can do the skill, this isn't super important, it's just the words really. And the more important thing is that you followed what we just did together. So happy days. Cool. How long was the video? 27 minutes. Oh, it's so long, but I hope you practiced though. Page 273, 5 to 10. Do a mix. Do a proper mix, buddies. You can do everything now. I hope that that's cool. You'll have to let me know in the chat how you feel about this. I might be able to give over a lesson as well, just a practice lesson only if you like, because we only have one more topic left till you're finished of the whole of my side of the course. So, brilliant work. And that's it for me. See you next time. Bye, buddies.